Okay, we are on to chapter 14. We got into yesterday just a little bit. And yesterday we talked about really kind of like phase changes and heating and cooling curves. It sort of brought together chapter 10 topic as well with it. So remember, you got kind of like a heating or cooling curve looks something like this. Again, what we looked at with water, so that was ice, which obviously is the solid version. That was liquid water there, and this was steam, which is gas. And remember, for water, that is 100 degrees Celsius, the normal boiling point, and 0 degrees Celsius there, the normal freezing point. And as we talked about, there is a certain amount of energy that's required to do nothing more than change a substance from one phase to the next. And those changes do occur at either the freezing point or boiling point of a substance. As we go from solid to liquid, or even going from liquid back to solid, the energy required to do that is what is known as the delta H of fusion, or the heat of fusion. And that is the energy required, as I mentioned, happening at that same temperature, just changing the substance. So we're not obviously changing the temperature. Remember, at something like the freezing point, there's both phases happening at the same time. So we talked about ice crystals sort of occurring. For water, and again, this is specific for water, 6.02 kilojoules per mole, are roughly 335 joules per gram is the heat of fusion. Now remember, that number is the same number regardless of which direction you're going, but this also ties back to what we talked about in chapter 10, which was exothermic and endothermic. So remember that delta H, or any type of energy sort of value that is exothermic, will have a negative value. So exothermic. And if a delta H, or any type of energy value like Q, for example, is positive, it will be an endothermic process. So when we talk about kind of going from solid to liquid, that's an endothermic process. You have to put energy in to do that, to like melt your ice cube. And that would be positive, again, 335 joules per gram. Again, if you're going from liquid back to ice, you got to release all that energy from the liquid. It's going to slow down the water molecules. They're going to kind of bunch together and go into the solid phase. Exact same number to do that transition, except that it's an exothermic process. And again, we would want to use the negative version of that. Same thing when we get here. This is our delta H of vaporization as we go from liquid to gas, or gas back to liquid. And again, for water specifically, it's roughly 40.6 kilojoules per mole, or that translates to about 2,260 joules per gram. Once again, something that we also talked about, a lot more energy required to do that transition, going from liquid to gas, than it is just going from solid to liquid. And again, as we talked about, by doing that transition into gas, we're completely breaking everybody apart from one another. So it does require a little bit more energy to do so. Same sort of idea in terms of the sign here as you go from liquid to gas, as endothermic. So that would be like a positive 2260 joules per gram and negative 2260 joules per gram if you are going from gas back to liquid. So whenever you're doing basically a phase change, and what that usually would entail is the temperature remains the same, but you just change the phase of something. That is when you look at a graph, as we talked about, these sort of plateaued lines, these flat lines on the graph. That means we're not changing temperature on this graph, but we are changing the phase. And again, that would be where you would use something like the delta H of vaporization or the delta H of fusion at those points. Now, we tied together again something we talked about in chapter 10, which is really the other part of this graph here. And in any of the parts where you are going pretty much vertically, kind of up, if you will, that is going to basically be a situation where you will be in the same phase, but you are changing the temperature. And to take care of the heat or energy associated with those transitions, again, it was a throwback equation there from chapter 10, Q is equal to ms delta T. So we use our specific heat equation anytime we're doing that type of transition where it is the same phase, but we're just changing the temperature. It's also important, especially in this chapter, probably where you have this kind of situation, this kind of heating and cooling, and you're actually changing phases. It's important when you look up the specific heat capacity or choose the specific heat capacity that you do grab it for the correct phase. So if you remember, we started with ice, I think, in that example. So we needed to actually use the specific heat capacity for ice, which is more like 2. Rather than the specific heat capacity for liquid water, which is 4.184. So you definitely want to make sure, depending on what phase you're in, that you do grab the correct specific heat capacity. Remember that we could do these things sort of in phases. So that was like our first step, second step, third step, fourth step, and like our fifth step as we went through that particular problem. And we could get the energy really associated with each of those steps along the way. And to get the total amount of energy, all we have to do is just simply add them all together, and that gives us our total amount of energy. Basically, we would get the same numerical value regardless of which way we went. Once again, the only difference would be the sign, as if we're going from solid to liquid to gas like we did in the example. That is all endothermic, and we should end up with positive numbers for everybody and a positive overall energy that's associated with that. If we started at gas and kind of went down to ice, those all exothermic processes to get us down there, and we should end up with negative values. Any questions on any of that there we talked about last time there? All right, so the next thing we're going to talk about is, nice, Jimmy. We're going to talk about intramolecular forces and intermolecular forces. So intramolecular forces, which we might have touched upon when we talked about gases, but intramolecular forces are the forces that hold one individual molecule together. So, for example, like covalent bonding, sharing of electrons, that is an intramolecular force. Opposite attraction, an ionic compound between the positive ion and the negative ion, that is also an intramolecular force. So if you have, like I might have used before, just one single sort of water molecule, when we talk about intramolecular forces, we're talking about really the covalent bonding here. And these guys here would be our intramolecular force within the molecule that basically holds that together. So that sharing of electrons between the oxygen and one of the hydrogens and the oxygen, the other hydrogen, is the intramolecular forces within this molecule that keeps it essentially from falling apart into pieces, basically. So that is the force that keeps this thing kind of together. And in the case of water, it is a covalent bonding, the sharing of electrons that's happening. Now, that is different than an intermolecular force. An intermolecular force is the force that holds one entire molecule together with another entire molecule. So that would be a situation where maybe you had not one water molecule, but you had two water molecules or multiple water molecules. And as we might have touched upon as well, water is polar, so the oxygen is more negative, hydrogen is more positive. And it is that attracted force between the negative side of one molecule and the positive side of another, and that is an intermolecular force. And it is the force that holds this particular molecule together with this particular molecule. And by the way, it does not have to be, like in this example, two of the same molecules. It is also could be two different molecules. So for example, it is the force that maybe holds together water and methanol when they get attracted to each other, again through the positive side of one, the negative side of another, like that. So that would be the force that holds this entire molecule together with this molecule. So the nice thing are really, when you talk about intermolecular forces, it is really just a simple interaction. All intermolecular forces are pretty much this interaction of the positive side of one molecule is attracted to the negative side of another. So no matter what type of intermolecular force it is, that is essentially what is happening. It is the opposite attracted, electrostatic attraction, positive side of one molecule attracted to the negative side of another, and that is essentially how all intermolecular forces basically work. Now, something that we did touch upon again when we were talking about gases is all intermolecular forces are always weaker than intramolecular forces. So any type of intermolecular force is always weaker than an intramolecular force. And the really easy example of that, again, is water, like I think we probably talked about there in the gas chapter as well. And for example, when you go to heat up water that's, say, in the liquid phase, the first bond that will actually break is the bond between this water molecule, for example, and the other water molecule, and that's the intermolecular force. That would allow, again, this water molecule and this one to basically enter into the gas phase. And we know that is true because, again, when you heat up some water to make pasta, you do not get like hydrogen gas and oxygen gas, right? You get basically steam, right? Which is still water. And that shows that basically the force between the water molecules are breaking. If the opposite was true, as we might have touched upon as well, if the opposite was true and the intramolecular force was weaker, when you would go heat up something like liquid water, you would start producing hydrogen gas, oxygen gas, which is not a great thing. And again, that intramolecular force is much, much stronger, so we don't have that happen. And we know that this doesn't occur, but it's actually this bond here that actually breaks. Any questions on that there? All right, so we're going to talk about different types of intermolecular forces. So all these forces that we're going to talk about are basically intermolecular forces. So the first type of intermolecular force is what is referred to as a dipole-dipole. And you might remember the word dipole from bonding. When things have a dipole moment, they are a polar molecule. So dipole-dipole is the main intermolecular force that is used by polar molecules with other polar molecules, or even with themselves, which obviously are also other polar molecules. And basically what happens is, because it is a polar molecule, there's an unequal sharing of electrons, and there is a negative side to that molecule and a positive side to that molecule. And basically what ends up happening is the negative side of one molecule is again attracted to the positive side of another molecule. And again, that is what keeps those guys together. Now, this is typically the one you find in polar molecules that cannot hydrogen bond. And we'll talk about hydrogen bonding in just a second. But they typically are polar molecules that lack the ability to hydrogen bond. When they get into, for example, the solid orientation or even the liquid orientation, they do try to move around as much as possible to maximize the positive and negative attractions to each other and minimize like positive and positive being near each other and negative sides of molecules and negative sides of molecules being near each other. No matter what they do, they will always have that situation occur. They're going to get some positives near each other, some negatives near each other, but they actually will continue to kind of move around and adjust until they're pretty happy with that as best they can get in that situation. They are only 1% as strong as covalent and ionic bonding, and that is because covalent and ionic bonding are intramolecular forces, as we just talked about. So they're much, much stronger than, obviously, this intermolecular force. So the main type of interaction that polar molecules do with themselves and other polar molecules, when they cannot hydrogen bond, is known as dipole-dipole interaction. Here's an example of that, I think.
Bonds between atoms with different electronegativities have a permanent dipole, that is, a separation of charges, because of the unequal sharing of electrons. Some molecules which contain polar bonds do not have a net dipole. For example, carbon tetrachloride has polar carbon-chloride bonds, but the polarities cancel as a result of its symmetrical structure. It is therefore a nonpolar molecule. Even though the chloroform molecule has a tetrahedral shape, one of the outer atoms is different from the others, so the molecule is not symmetrical. This means the bond dipoles do not cancel, and the molecule has an overall dipole moment. It is polar. Molecules such as sulfur dioxide have asymmetrical structures due to one or more unshared pairs of electrons on the central atom. Sulfur dioxide is an asymmetrical molecule with polar bonds, therefore it is a polar molecule. When polar molecules such as sulfur dioxide are close to one another, they tend to align so that the positive end of one molecule points towards the negative end of another molecule. Attractions among polar molecules are called dipole-dipole forces.
So again, as you saw there in that animation, they do try to move around and really sort of maximize that opposite attraction and kind of minimize as best they can that kind of similar attraction that's going to happen. Now, another type of intermolecular force, which is known as hydrogen bonding, is actually a dipole-dipole interaction. It is a special type of dipole-dipole interaction. It's a relatively strong attraction, and it has its sort of own category, even though it technically is still dipole-dipole sort of interaction that's happening. And hydrogen bonding occurs when you have a molecule that is polar, or it has at least a bond where the hydrogen is directly attached to either nitrogen, oxygen, or fluorine. So that is how you know, for example, if something has the ability to hydrogen bond, that hydrogen does need to be directly attached in that molecule to one of those three elements. If you look at the periodic table where we have those elements are nitrogen, oxygen, and fluorine. That is upper right of the periodic table. Those are our three kind of most electronegative atoms. And because they're really electronegative, when it hooks up with hydrogen, it's going to create a pretty good separation of charge, and it's going to make this really strong sort of attraction that occurs. So if we look at water, which we were looking at a second ago, it can hydrogen bond, and that is actually the intermolecular force that water does between the negative and the positive of the other. This is hydrogen bonding occurring. And that is because this hydrogen is directly attached to an oxygen. Same thing with any of these hydrogens, they're directly attached to an oxygen. So it has the ability to hydrogen bond. It is also what is happening when you take water and you attach it to something like I drew earlier, maybe something like methanol here. Again, this methanol, although this part of it is non-polar because it's carbon and hydrogens, it is this hydrogen that has the ability to hydrogen bond because it's part of this polar bond here. And that actually matches exactly like the polar bond we see there. And now these two guys can hydrogen bond. So it is important to remember that just because you do have hydrogen, it doesn't mean you could hydrogen bond. So like I think it might have been one of the examples there, if you take something like methane, methane has a ton of hydrogens, but all these hydrogens are non-polar, and none of these hydrogens are attached directly to nitrogen, oxygen, or fluorine. So even though it's got a bunch of hydrogens, they're basically non-polar. And if you remember, non-polar basically means equal sharing of electrons, which basically means a neutral bond, right? There's really no positive side or negative side. And because of that, it cannot hydrogen bond in this case. So this guy cannot hydrogen bond, even though it's got a lot of hydrogens. Yeah, you had a question? Yeah, so it can only occur when the molecule itself has a bond that has a hydrogen that is directly attached to either nitrogen, oxygen, or fluorine. So, for example, like in that little animation, HF, right? This guy can hydrogen bond because this hydrogen is directly attached to the fluorine. And because of the difference in electronegativity, what that creates is a pretty good separation of charge. And that's going to be very important for it to interact with other molecules through hydrogen bonding. By the way, if you had something like ammonia here, right, if you drew ammonia, the hydrogens in ammonia can hydrogen bond as well because hydrogen directly attached to the nitrogen. By the way, any of those hydrogens can do it because they're all attached to the nitrogen. But ammonia is another example of something that can hydrogen bond because of that. So that is, this part right here is really an important part. And sometimes people, when they hear the name hydrogen bond, they think all you need is a hydrogen. But it does need to be a hydrogen that, again, is directly attached to one of those three elements. Yeah. It is always a polar molecule. And remember, in most cases, it will have lone pairs on the central atom. But also, like in that example, you know, if you took the carbon with the, too many carbons there, carbon with the fluorine and the hydrogen here, right? This is this is actually a polar molecule, right? And it doesn't have any lone pairs on the central atom, if that's what you're asking. But what it does have is unequal overall sharing of electrons. So really what we're talking about here in a lot of cases is molecular polarity as a whole. And this guy would be considered a polar molecule where you would draw, for example, that dipole moment arrow heading towards the fluorines. And that basically means in this case, this molecule near the fluorine side is more negative, and near kind of the hydrogen side is more positive, and that's what will allow it to sort of do that dipole-dipole interaction. This guy cannot hydrogen bond, even though it does have a hydrogen, and it's because that hydrogen is directly attached to the carbon in this case. So this guy would have to do the previous slide, the dipole-dipole interaction. And that's what I was said before in the previous slide. Dipole-dipole interaction is for polar molecules that cannot hydrogen bond. So something like this, which is a polar molecule, would fall under the category of dipole-dipole. It would not fall under the category of hydrogen bonding because it doesn't have the ability to do so. While ammonia, like HF, or even water here, all those, or even this guy, methanol that I drew as well, all those guys are polar molecules, but they have the ability to hydrogen bond. So the best classification of their intermolecular force would be hydrogen bonding versus, say, dipole-dipole. Even though hydrogen bonding is sort of a class of dipole-dipole, but it is sort of almost like its own sort of intermolecular force, even though it's really the same thing happening, and it's basically dipole-dipole, but it's a special class of it. Is actually hydrogen bonding is actually the strongest intermolecular force you could have between like hydrogen bonding and dipole-dipole. They're close, but hydrogen bonding is actually stronger. No, hydrogen bonding is actually the strongest. Yeah. So hydrogen bond is actually the strongest of the intermolecular forces. And that's why, for example, things that can hydrogen bond typically have very high boiling points and melting points. And that's because it's held together pretty tightly and stuff like that. Yeah. Sure. Yeah. So all these are intermolecular forces, which by definition means molecule and molecules coming together. Now, it's sometimes confusing. Sometimes people miss this part of it. For example, if we're talking about water sort of interacting with itself, other water molecules, it's hydrogen bonding that's happening between like a water molecule and itself. But hydrogen bonding could also describe what's happening, like I drew here, over here on the right-hand side, where we have two different molecules coming together. Those two different molecules are also interacting with themselves through hydrogen bonding as well. So it could, when we talk about intermolecular forces, it can account for like one molecule sort of interacting with itself and other same type of molecules, and it also can account for how it interacts with different types of molecules. But intermolecular forces, by definition, is the force that holds two kind of molecules together. And why is intermolecular forces important for, say, this interaction here? It is actually what accounts for example, things being soluble in each other and being able to mix in each other. So if you took something like methanol and you took something like water, it actually would mix and be soluble in each other because they're both using hydrogen bonding. So things, and I think we might have saw it earlier, and we'll see it maybe in 15 or 6, one of those chapters. But the saying of what is sometimes referred to as like dissolves like. So things that use similar types of intermolecular forces will be very soluble in other molecules that use the same type of forces. So that's why, when, for example, you put water together with methanol, they'll mix because they both use hydrogen bonding. If you take water together with oil, the oil uses a much different type of intermolecular force. They will not mix because they're very, very different. So it accounts for intermolecular forces accounts for things like boiling points and melting points and freezing points for a substance. It also accounts for solubility and how it's able to interact or not interact with other different types of molecules. Questions on that there? So let's take a look at this here.
Some polar molecules have unusually strong intermolecular attractions called hydrogen bonding. These attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid states of these substances is determined by hydrogen bonding. The hydrogen atom in hydrogen fluoride is attracted to the fluorine atom on another hydrogen fluoride molecule. Water, with 2 hydrogen atoms and 2 unshared pairs of electrons, can form 4 hydrogen bonds per molecule. In ice, hydrogen bonding leads to a tetrahedral arrangement of water molecules around one another, forming 6-membered rings that leave open channels through the ring structure. In liquid water, the tetrahedral arrangement is not fixed because the molecules are able to move around, and on average, a water molecule is surrounded by 3.4 other water molecules. Hydrogen bonding forces are unusually strong attractions that occur among molecules in which hydrogen is bonded to a highly electronegative atom.
So as we saw in that, that also shows you what we were talking about at the beginning of the chapter with ice and all those sort of empty spaces. Because hydrogen bonding is a relatively strong intermolecular force, what happens is when it gets down to ice, the water molecules no longer have enough energy to move around and they get kind of locked into place, creating all that openness between the water molecules, which is why, as we talked about at the beginning of the chapter, ice is less dense than liquid water because of that. In the liquid phase, the water molecules still have enough energy to kind of overcome that rigidness of that strong bond and get closer to one another and not create as much open space between the different water molecules. And again, here's some examples of hydrogen bonding. Again, the negative side of one molecule, the positive side of another here happening. Now, another type of interaction, since we're talking about dipole, and something that you've seen before, is what is sometimes referred to as an ion dipole interaction. And an ion dipole interaction is pretty much what happens, for example, when you go and dissolve something in water. So if you took something like sodium chloride and you dissolved it in water, what ends up happening, as we've talked about, I think previously, is we have our sodium ions and we have our chloride ions. And basically what happens in this case is, because water is a polar molecule, again having a negative side and a positive side, the negative side of water will be attracted to the positive ion or the cation, again through that opposite attraction, while the positive side of water, which is the hydrogen, will be attracted to the negative side or negative ion in this particular case as well. So this is another type of intermolecular force. And as we talked about, that is essentially how something dissolves, right? As we talked about, what happens is there's just so many water molecules that surround those guys, it is no longer visible to us, right? The solid that's there. And now we have basically a solution that occurs as this dissolves. So this is another intermolecular force that we see a lot when you dissolve something in water, for example, and you have ions doing that. Let me questions on that there. And again, that is just because we have a lot of water molecules that they're able to kind of pluck off those ions. Remember, without those water molecules there, that attraction force between the sodium ion and the chloride ion are definitely going to come back together because of that intramolecular force. Now let's talk about the next type of intermolecular force, and this is what is known as dispersion forces. And dispersion forces are pretty much your main force for nonpolar molecules interacting with nonpolar molecules. So nonpolar molecules are basically going to use dispersion forces as their main source. It's sometimes referred to as London dispersion forces. And these are relatively weakest forces. So out of all those sort of intermolecular forces, hydrogen bonding, dipole, and dispersion forces are actually the weakest of all of them. And it's because they are temporary forces, are accidental forces that occur. So how does that happen? Well, for example, if you have a nonpolar molecule, it basically is neutral. It does not have a charge, right? And that's because overall it has equal sharing of electrons that are happening. So one way that you can make dispersion forces happen is you can induce it. And it is sometimes referred to, for example, as an ion-induced dipole. And what that means is if I took a positive ion and it rolled up on my nonpolar molecule here, what's going to happen is the electrons in that nonpolar molecule are going to be attracted to that positive ion. And what that's going to temporarily do in this case is create a temporarily negative charge and positive charge on my nonpolar molecule, which is going to work really well because now these two guys have a way to interact with each other. It is temporary because if that ion kind of floats away, there goes that separation of charge in the nonpolar molecule. It's going to kind of go back to kind of being neutral as well. You could also do this with a polar molecule. If you had a nonpolar molecule and you rolled up a polar molecule next to it, once again, in this case, the negative side of that polar molecule is going to make the electrons in this guy run to the opposite side. And again, it's going to create a temporary charge in your nonpolar molecule that will temporarily be able to interact with our polar molecule. This is what is referred to as a dipole-induced dipole interaction. So this is one way in which, for example, a nonpolar molecule can basically interact with a polar molecule. The idea of this, for example, is like oil, which is nonpolar, it uses dispersion forces. If you ever done oil and vinegar salad dressing or something like that, right? You mix it up. And again, for a short period of time, it will stay mixed, right? But over the long period of time, if you just leave the bottle, everybody's going to separate out, right? The oil part and the water part is going to separate out from each other. And it's because they cannot maintain that interaction over the long period of time. So there's a slight interaction that can happen, but they won't be able to basically maintain it. Another way that this could happen is actually with two nonpolar molecules. So if you started with two nonpolar molecules, they both are essentially neutral. Now, what can happen, for example, in this first nonpolar molecule is all the electrons that are flying around, just by circumstance, ends up going to the left-hand side of this molecule because they're flying. They all just kind of vacation together there on the left-hand side of the molecule. That is on the left-hand side of the molecule going to temporarily create a separation of charge, which if it is still next to this other nonpolar molecule, is going to cause the electrons in this guy to now be attracted to that positive side. And now our two nonpolar molecules that started out with no charge, they will now both temporarily gain a charge. And now because they temporarily gained a charge, they will have a way to basically interact with one another. And now they're able to basically interact through that positive and negative side. This again is temporary because as soon as those electrons kind of shift back, that interaction is going to break apart and a new one's going to form and that's going to break apart. And you got these kind of new interactions breaking apart, new interactions breaking apart. Once again, they cannot maintain that. The ability at which electrons can kind of do that is what is known as polarizability. And it does increase with molar mass. So the higher the molar mass of a nonpolar compound, the stronger the dispersion forces will be. So if you're comparing between two nonpolar molecules, they are going to use dispersion forces as their main intermolecular force. And if you want to know which one is stronger intermolecular force between the two nonpolar molecules, it is the one with the larger molar mass. And that's because if you have a larger molar mass, you will have more electrons. More electrons means more places for it to interact, and also greater chance of those electrons kind of going one way or the other because there's just more of them in that case. So dispersion forces strength increases with increasing molar mass. And again, because of the availability of your electrons. Now, can everybody, polar molecules and nonpolar molecules, use dispersion forces? As we see on the left there, they can, yeah? So technically speaking, everybody can use dispersion forces, polar molecules and nonpolar molecules. But it is really the main force for nonpolar molecules. For polar molecules, they're going to use either dipole-dipole or hydrogen bonding. So if you're asked, for example, what is the strongest intermolecular force for water, hydrogen bonding should be the correct answer. Even though it could technically be dipole-dipole and it could technically do dispersion forces, it is not the main one it's going to use. For nonpolar molecules, it is the main one that it could use. It is the only one it could use. This again is why, as I mentioned a second ago, water and oil, they do not mix because, again, water wants to use hydrogen bonding, which is a relatively strong intermolecular force. Oil wants to use dispersion forces. They are not going to be able to maintain that interaction over the long period of time. That is also why, for example, water is a pretty crappy solvent for things that are nonpolar, because if you take water and you try to dissolve something that's nonpolar in it, it is not going to mix. Perhaps you remember, or you did that experiment a while back where you have the different layers where with the halogens, they separated out because of that. So earlier we saw this guy, which is methane, which, as we talked about, could not hydrogen bond. But because this is a nonpolar molecule, it would use dispersion forces as its main force. Now, in terms of strength, we'll take a look at this one here.
Solid carbon dioxide, dry ice. Nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary separation of charges, a dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. These attractive forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
So here's an example of an instantaneous dipole. Again, a nonpolar molecule, electrons kind of separate out, get a temporary charge, going to influence this other nonpolar molecule to get a charge. And now the positive side of one and the negative side of the other are going to be able to be attracted to each other temporarily. Now, when we talk about intermolecular forces, I'll do it here. we basically have three main types of intermolecular forces. We have hydrogen bonding, which again is the main force that polar molecules and polar molecules will use that have the ability to hydrogen bond. And again, that means to have the ability to hydrogen bond, you need a hydrogen directly attached to either nitrogen, oxygen, or fluorine. So again, that is what you need for that to occur. An example of that is water. Yeah. We have dipole-dipole interaction. And this is the main force for polar molecules and other polar molecules, or even itself, that cannot hydrogen bond. So an example of that is SO2. Again, if you drew SO2, looks like that, a little unsymmetrical geometry, right? It's going to be a polar molecule, it has the ability to do that. It doesn't contain any hydrogens, by the way, right? So it cannot hydrogen bond, but it is polar, so it will be able to do that. And obviously here we have our hydrogen directly attached to our oxygen. And then we have dispersion forces, which is your main nonpolar interaction. And an example of that, take your pick, like CO2 we just saw there in the animation. It has polar bonds because of the geometry. It is nonpolar. Or any type of organic molecule that's just carbons and hydrogens like methane will also use dispersion forces. Now, in terms of the strengths of these three intermolecular forces, as I mentioned earlier, your hydrogen bonding is the strongest. Your dispersion forces are actually the weakest forces that can occur. And again, the things that this affects is things like melting points and boiling points. You would expect a relatively high melting point, boiling point, compared to on this end, a much lower melting point and boiling point sort of situation. So again, if you're comparing somebody that can hydrogen bond to somebody that's using dispersion forces, it's every day the hydrogen bonding guy is going to have the higher boiling point and melting point, and the guy with the dispersion one should have the weakest. Again, if you're comparing even a dipole-dipole to a dispersion force in terms of melting points and boiling points, the dipole-dipole should be higher than the dispersion forces. Once again, though, if you are comparing two nonpolar molecules and seeing which one would have the higher boiling point or melting point, again, the one with the higher molar mass would have the higher boiling point and melting point if you're comparing, again, two nonpolar molecules together. So if you're comparing two nonpolar molecules where they both are using dispersion forces as their main force, the one with the higher molar mass, which has more electrons and more interaction points, will have a higher boiling point and melting point when you're doing that. As I also mentioned before, this idea we'll hear in another chapter as well, but like dissolves like. So things that use similar intermolecular forces that they use with themselves will be really soluble and mix well with others. So what that usually means is if you have an ionic guy and a polar thing, they're going to be pretty soluble in each other. If you have a polar thing and a polar thing coming together, they're going to be pretty soluble in each other. If you have a nonpolar and a nonpolar guy together, it's going to be soluble. Again, you only get into some trouble here if you kind of cross over polar and nonpolar. Typically, these guys are going to be insoluble in each other. They're not going to really mix. Again, because what you're going to have is pretty dramatic difference in how they want to interact with each other. Again, you're going to want a hydrogen bond or dipole versus somebody who wants a dispersion force. Any questions on intermolecular forces here and the differences between them? So sometimes when you're trying to decide, for example, what, if you come across a question, you're trying to decide like, what is the main intermolecular force for this thing? Sometimes just a quick drawing of the Lewis structure, if you're not sure, can help you out and remember, like we talked about, is it symmetrical? Is it unsymmetrical sort of geometry? And that will help you decide maybe if you're not sure if that thing is polar or non-polar molecule. That will kind of help you just a kind of a quick Lewis structure sketch, and like you're going to do like molecular polarity and try to decide is it polar or non-polar, then that should then scoot you hopefully to the sort of the right answer there. Any questions on that? Yeah.
Down there, like if I'm trying to decide polarity of just right from the bipolar, right?
Yeah, so you can in probably most cases, kind of like what we talked about with molecular polarity, keep it super like simple. Like you look at this and you draw and go, okay, I got dots on the central atom, right? Everything on the outside is the same. That's probably going to be a polar molecule. That then should put you to one of these two options, right? And when you look at it, obviously it doesn't have a hydrogen, so that should then eliminate this guy, right? And it would has to be dipole. And if you had something like water here, right? We see dots, we see things on the outside is the same. It's definitely going to be polar, so that takes you to one of these. Should eliminate dispersion forces because it's polar. And at this point you go, oh, it does have hydrogen. So the next thing you want to think about is that hydrogen attached to a nitrogen, oxygen, or fluorine? And it is, then that should then move you back to hydrogen bonding. As opposed to if you had like this guy here, like our methane, you could look at it and go, that is symmetrical geometry, no dots. Everything on the outside is the same. It's going to be non-polar. Right there, that's all you need to know pretty much. That's going to put you right there. That should be your choice. So, or even like this here, the CO2, again, that's linear. Even though it has polar bonds, the geometry is going to make it non-polar. So again, that should put you here. So if you could pretty much identify that molecule as being non-polar, and it's asking about how it's going to interact with itself, you could pretty much just head to dispersion forces as the main force. If you have a polar molecule and they were asking how it's going to interact with itself or really other things, then you have to kind of take the additional step of it's either going to be hydrogen bonding or dipole. Can it hydrogen bond or not is kind of what you want to kind of look at. Other questions? Yeah. So another thing we're going to talk about is some of those processes that occur that we talked about a little bit earlier. Vaporization or evaporization does occur when really the liquid molecules gain enough energy to escape the liquid phase. By the way, you have evaporation occurring at the surface of a liquid at all times. That is why, for example, if you have a liquid, right, at the surface, you have things jumping out of the liquid phase, and you got things dropping back into the liquid phase. And that is happening at the surface of any liquid that you have. That is also why, for example, right, if you put like a little drop of liquid there on the bench, right, eventually it will evaporate if you don't do anything. And that is because you have all this evaporation occurring, but you also have air, which moves those guys out of the way, which means they're no longer available to drop back into the liquid phase because it got blown away. And eventually what will happen is you'll have a greater rate of evaporation than you do condensation, and eventually your little drop will eventually evaporate out. There's a lot of surface area where that's happening at once, which helps it out. That's also why if you put a liquid in a beaker, right, it'd take much longer for it to evaporate, right? Because on the surface, molecules are able to kind of do that. All the ones underneath got to work their way to the surface to kind of do that. So it'll take a much longer time for that to happen. Obviously, evaporation and vaporization is the transition from liquid to gas. And obviously going in the opposite direction from gas to liquid is condensation. So that is evaporation, and going in the opposite direction is condensation. So when gas molecules are flying around, they lose enough energy. When they hit each other, they stick. because they don't have enough energy basically to escape one another, and they drop back into the liquid phase, and you get condensation that basically occurs. The pressure of a vapor at equilibrium is known as the vapor pressure. Liquids with high vapor pressure are said to be volatile. So the only way you could have high vapor pressure is you have a lot of gas molecules above the liquid, and the only way for you to get a lot of gas molecules above the liquid is the liquid to start evaporating, right? So that's what volatile means. The vapor pressure of liquid is determined by its intermolecular forces. So if you have a large vapor pressure, and those are basically the liquid molecules that escaped into the gas phase above the liquid, that means that your intermolecular force here is probably relatively weak if you have a high vapor pressure, because that's going to allow those guys to escape the liquid phase. If you have a low vapor pressure, you probably have a much stronger intermolecular force, because most of them are going to stay together in the liquid phase and not escape. So the stronger the intermolecular force, the less molecules can escape the liquid phase. You'll have less gas molecules above the liquid and a lower vapor pressure. The weaker the intermolecular force, you will have a much higher amount of molecules to escape into the gas phase and a higher vapor pressure. Again, right, pressure related to collisions, and collisions would be related to the number of gas molecules present. So if you have more gas molecules, more collisions; less gas molecules, less collisions. Now, when we put a liquid in a closed container, a couple of things occur in a closed container. We will eventually start at the beginning, have pretty much just evaporation occurring, right? So we'll have a pretty high rate of evaporation. The problem with a closed container is these guys don't have an escape route, right? They're closed off. So what will eventually happen is these guys will U-turn and start heading back down into the liquid phase. So you'll get some of those guys dropping back into the liquid phase. And it will continue until equilibrium is reached. And basically what equilibrium means is the rate of evaporation will equal the rate of condensation. And when equilibrium is reached, you will have some gas molecules now above the liquid. And as these gas molecules here, they're creating the vapor pressure that would be associated with, obviously, that liquid, is all those gas molecules above it. One of the things that you will usually notice, and sometimes you can see it more than other times, but if you looked at the actual liquid volume when you first filled the flask here, and you look at it when it reaches equilibrium, it actually will drop volume a little bit. And that is because when you first put the liquid in there, everybody was in the liquid phase. When it reaches equilibrium, some of those guys that originally were liquids are now flying around as gas molecules above the liquid phase, and that will result in a little bit of a lowering of the liquid volume in your actual flask. This prevents evaporation, right? Because we have a lid on it. If we obviously took the lid off, that would give these guys an escape route, right? And the air could blow them away, which means they would not come back to the liquid phase. And eventually, right, it will eventually start to evaporate, right? And evaporate and evaporate. It may completely evaporate. And as I mentioned a second ago, kind of like if you have a drop of something on a bench, it will eventually evaporate again, because you have a lot of surface area where that can evaporate from, and that's going to prevent that air blowing those guys away, prevent them from coming back into the liquid phase. Any questions on that there? Okay, we are going to get started here. We are then rolling back to chapter 11 that we kind of skipped over for a bit. This, I think, was maybe last week's, is where the handout is on this one and that module. All right, so chapter 11 talks really about modern atomic theory, and really what we're going to be focusing in on a lot in this chapter are electrons. And the chapter deals with electron configuration. I think it also deals with some periodic trends as well. But ultimately what we will be talking about in a majority of sort of this chapter is a pretty straightforward idea of what is happening. So, for example, if we have some different energy levels, electrons, if this arrow represents an electron, can be found at different energy levels. And there are certain situations that occur that will perhaps excite an electron from a lower set of energy to a higher set of energy. And ultimately, what happens in chemistry and pretty much in life as well, things like to be in the lowest state of energy, and that's sort of the most stable sort of situation to occur. So when electrons do get excited up to higher energy levels, they really are not so happy with being up there. They do want to eventually work their way back down to a lower energy level. And one of the ideas of the law of conservation of energy is we don't create nor destroy energy, but it can be transformed from one place to the next. So what ends up happening, for example, here is as the electrons are transitioning down to a lower energy level, the atom itself has to give off that energy, as we'll talk about in terms of a photon of light. And it basically will give off that energy as a wave. Now, in certain cases, that energy that's coming off, that's being given off as a wave, can correspond, for example, to the visible part of the spectrum. And that is where we see colors like Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. That is basically what happens, for example, when you did your flame test in that experiment we did earlier. You excited the electrons by putting it into the fire. It gained a lot of energy, excited all those electrons to a higher energy level, and basically relaxed back down. When that process, it'll give off a distinct color. You probably also have done a flame test, maybe if you've ever boiled water and it overboiled and it hit like the flame on your stove. If you had a gas flame, the flame probably changed color to orangey as it hit, and it's the sodium that's basically being excited at that point. And more recently, last week, where you probably watch fireworks, right? And you watch fireworks there as they launch those things in the air. They have different elements as they explode, gains a lot of energy. All those elements and those electrons, as they relax back down, we see pretty colors like red, orange, blue, and all those type of colors that occurs. So a lot of what we're going to focus on pretty much in this chapter are electrons. And ultimately, this is sort of the overall idea of sort of what's happening is this sort of transition of those electrons to lower energy levels, and will give off some energy in the form of light. So we remember our friend Rutherford and basically described an atom as barely having a positive core, which is known as the nucleus. As we know, within the nucleus is our protons, which are positively charged, also our neutrons, which have no charge. And moving out from the nucleus at some point where we have our positive and protons and our neutrons, we have our electrons. And one of the things that will come about from our conversation is the idea that electrons are pretty much randomly sort of flying around in that empty space of the atom. As we also talked about, because electrons are negatively charged and because the nucleus ultimately is positively charged, there is some attraction between those electrons and the nucleus. And that's what's going to prevent, for example, the electrons from just leaving, right? It's going to prevent them from just flying away. There is some type of attraction to sort of the nucleus that is there. Now, one of the earliest sort of ideas of sort of energy and how energy sort of moves around was done by a guy named Planck. And in 1900s, he did a lot of work with radiation. And what Planck's work showed was that energy typically can be released and absorbed pretty much in definite amounts. And these sort of definite amounts or packets of energy is sometimes referred to is what is known as a quantum of energy or a quanta of energy. And the idea behind quantized energy is pretty much this idea of, for example, if we take our electron that's on this energy level and it wants to perhaps go to the next energy level, this electron will gain enough energy to completely make that transition. So completely get from one energy level to the next. And it also works in the opposite sort of direction, go from a higher energy level to a lower energy level. It will lose enough energy to completely make that transition. The idea of quantized energy is, and we'll see a better picture of it a little later on, but you could think of it like stairs, right? The idea with stairs is you're either on like this step, this step, this step, or that step. You don't walk upstairs or downstairs and decide, I'll just hang out in between steps, right? Because you're going to fall. And that's essentially the idea of quantized energy. Either the electron will be on this energy level, it'll be on that energy level, that energy level. You won't find an electron just kind of hanging out in between. They will gain enough or lose enough energy to fully make that transition from one energy level to the next. Now, Planck's quantum theory talked about radiation, and radiation is the emission and transmission through space of energy in the form of waves. So when we talk about energy moving through space, we talk about it moving as a wave. So with that being said, let's talk a little bit about waves and some parts of waves. And some properties of waves which are important is a wave can be thought of as a vibrating disturbance where energy is transmitted. Here's our bird hanging out at the beach, right? And the wave's actually moving past the bird. He's going up and down, but the wave is actually moving. If you've ever been in the ocean, right, and you got hit by a wave, you know it has a lot of energy sometimes, right, when that wave hits you. And sometimes you can kind of just sit there and let it kind of float past you, right? So that is energy being moved through space in the form of a wave. And the waves, as I mentioned, does have some characteristics that we should be familiar with. So let's talk a little bit about those. First off, lambda, which is the abbreviation for the wavelength, that is basically two peaks or troughs. So that is the distance between two peaks. Or really, even if I fix that guy up there, two troughs, whichever way you want to go there. So the wavelength is, again, that situation there. Wavelength is very typically given in meters, nanometers, and centimeters are common units of wavelength. Remember that nano is 10 to the minus 9, right? So that's a very common conversion that's used a lot of times with wavelength. Most waves are given in meters, but when we talk about colors like red, orange, yellow, green, all those guys, they very often are given in nanometers. The frequency, which is abbreviated as a nu, is not really a V, but sometimes people call it a V, but it's not, is the number of waves that pass through a point in a particular second. It is measured in a couple of units. It is measured in reciprocal seconds or a hertz. And a hertz is equal to a reciprocal second. They are a one-to-one relationship between those two things. Frequency, again, is how many times it passes a point in a particular point in time. The amplitude is the vertical distance there from the bottom to the top of your wave. And one way you could calculate the speed of a wave is take the wavelength times the frequency. Wavelength is in meters. Frequency is in reciprocal seconds, which typically gives you a speed of a wave in meters per second, which is the typical units associated with a wave. Questions on that there? Now, light behaves like electromagnetic radiation, which means the emission of energy in the form of these waves. Electromagnetic radiation can sometimes have properties that are characteristic of particles. And a lot of what happens, and we talk about in this sort of chapter, is what is sometimes referred to as the dual nature of light. And a lot of things, like light, for example, and waves, can have wave-like function, but we also could think of waves as having particle-like function and vice versa. Particles could have wave-like function, and particles obviously could have particle-like function as well. So that is the wave particle nature of light. We could apply sort of wave function and think of particles like electrons, for example, as behaving like waves. And obviously, waves can behave like particles as well. Now, we could think of a beam of light traveling through space as a tiny packet of energy, which are called photons. There is a relationship between the wavelength and the frequency and also the energy. So if you have a wave that has a fairly long wavelength, so if we have something like this, where we have a fairly long wavelength, if the wavelength is long, typically the frequency is lower. And that usually means that we have a lower energy associated with that. And that is different than if we had a much smaller wavelength here. So if our wavelength is small, or short, I guess is the way to do that. We typically will have a much higher frequency, and that is usually associated with a much higher energy. So the higher the frequency, the shorter the wavelength, the higher the energy, and vice versa. The longer the wavelength, the lower the frequency, and the lower the energy. So again, there's that relationship when we look at wavelength and frequency to energy. And that goes for all types of light and electromagnetic radiation, like even colors. There is a difference between the energy of, say, red and purple based on their wavelength and their frequency. So here again is light that's behaving like a wave, but we could also have it as like a stream of packets of particles that's happening here as well. And again here in between red versus blue, blue has a much smaller wavelength, which means higher energy than our longer wavelength of red. Now, one thing that is common to all electromagnetic waves is the speed at which they travel, and that is the speed of light. And here they would like you to know this number, not the 3 times 10 to the 8 that most people use, but they would like you to know 2.9979 times 10 to the 8 meters per second. So that is something you should know through your chemistry journey here. And again, a lot of times people will round that to 3 times 10 to the 8, but here they do want you to use 2.9979 times 10 to the 8 meters per second. That is c, which is the speed of light. That's about 186,000 miles per second, which is pretty fast, I would say. When dealing with electromagnetic waves, that equation that we saw earlier can be shortened into c is equal to the wavelength times the frequency. And since c is a constant, that means that if you know the wavelength of your wave, you can figure out the frequency, or if you know the frequency, you can figure out the wavelength. The good news is it's the same calculation regardless of which one you're solving for. You take c divided by the other one that you're given. So if you want the wavelength, c divided by the frequency, and if you want the frequency, c divided by the wavelength. I will say that if you do this spot right here, you do need to be careful because the units of c is meters per second. So this guy needs to be in meters if you're using this equation so that it will cancel out correctly with the meters per second above it. So again, I would say sometimes centimeters, but a lot of times you might be given a wavelength in nanometers. So that nano conversion is used a lot in this situation. So this allows us, like I just said, if you know the wavelength or the frequency, you could use this equation here basically to figure out the opposite one that you do not know. So why don't we try one here and see what you come up with. What is the frequency for a wave with a wavelength of 4.68 times 10 to the minus 7 meters? So, okay, so let's take a look. We're looking for the frequency. In this case, we are given the wavelength, which is 4.68 times 10 to the minus 7 meters. And again, a number that we always have available to us is the speed of light, 2.9979, I think, times 10 to the 8 meters per second. So using our equation, c is equal to wavelength times the frequency. We're going to solve for the frequency by dividing that to the other side. So our frequency would equal c divided by the wavelength. In this case, that's already in meters, which is going to work good for that one as well. So putting that in there, going to give us 2.9979 times 10 to the 8 meters per second divided by 4.68 times 10 to the minus 7 meters. The meters will cancel. That is going to leave us reciprocal seconds. We definitely want to make sure we use our exponent button in this case, and we will end up with 6.41 times 10 to the 14. And this is reciprocal seconds are basically 1 over seconds, right? Is our units in this case, right? Question on that calculation there. All right, so definitely make sure exponent button when you're punching these guys in. Let's take a look at another one here, I think. What is the wavelength in nanometers for a wave that has a frequency of 5.6 times 10 to 14 hertz? Once again, nano is 10 to the minus 9. So see what you come up with on this one here. Here we are looking for the wavelength. And in this case, we are given the frequency, which is 5.6 times 10 to the 14 hertz. Remember that that is a common unit of frequency, which is a hertz. Like in your radio when you listen to megahertz on a radio station. But 1 hertz is equal to 1 reciprocal second, so it is a 1-to-1 relationship. So that is the same as 5.6 times 10 to the 14 reciprocal seconds. And again, we still have our c, which is a constant, 2.9979 times 10 to the 8 meters per second. Once again, here our wavelength will be c divided by the frequency, rearranging that equation, taking our 2.9979 times 10 to the 8 meters per second, divided by our frequency of 5.6 times 10 to the 14 reciprocal seconds. Those guys are going to cancel, and that's going to leave me meters when I do this. And we will end up with too many zeros to count. We will end up with 5.35 times 10 to the minus 7 meters. Again, here, though, we are looking for nanometers. So remember that when you see this or use this, we want to use it correctly. So that is in 1 nanometer, there are 10 to the minus 9 meters. Again, that is the correct way to use that. That would mean if we'd use that as a conversion factor here, we want meters on the bottom so they cancel. And we would take this basically and divide by 1 times 10 to the minus 9. And that's going to give us a 535 nanometers in this case. Yeah. Any questions on that one there? So again, common errors people make, not using the exponent button and getting something like the nanometer conversion backwards, right? So just got to be careful on that. Any questions on how to calculate wavelength or frequency? Yes, sir. Yeah. It's a one-to-one relationship between those. So if you had to convert between those two units, basically same number, just change the units. Yeah. If your question is, what does that mean? It basically means 1/seconds, basically. It's the same thing as that, yeah.
You always switch your units from hertz.
You don't really have to, but it might be helpful because technically it's C's in meters per second. So that just might help you recognize that those should cancel. They technically should because, again, it's a one-to-one relationship between those. Yeah. Other questions? So speaking of this, when we talk about those electrons, for example, sort of transitioning from one energy level to the next, or any wave in general, we'll have a specific wavelength that corresponds to what is known as the electromagnetic spectrum. And depending on where that sort of wavelength falls as to what you might observe. So for example, when we look at just the wavelengths here, this is 10 to the fourth versus 10 to the minus 12. This side over here has a much longer wavelength, which means it should have a lower frequency and also a lower energy, as opposed to over here where we have a shorter wavelength, a higher frequency, and that usually results in higher energy. So as we kind of go in this direction on this graph here, we're increasing energy, we're decreasing wavelength, it's getting shorter. So over here on, I should pick a better color that doesn't blend. We'll go, maybe we'll go red. So over here we have radio waves. So that's like listening to your radio in the car. You got your FM, AM, cellular sort of in that area. And as we continue down here, the next sort of area is microwaves. So as we get to microwaves, we're getting a little shorter of a wavelength, which means it has more energy and has enough energy, for example, to spin your water molecules in your frozen pizza really fast. And you get a pizza like in 2 minutes, right? So that's a good aspect of that, right? So it has enough energy to really make those water molecules move really, really fast in there. If you continue down the road here, a little shorter of wavelength again, we get into the infrared part of the spectrum. That's usually where we feel heat and that type of situation happening. If you go past the infrared, we then get into the visible part of the spectrum. This is where we see colors. So like the fireworks example, your flame test, those are basically what we're seeing is waves coming off that fall in this part of the spectrum here. And that is our Roy G. Biv, right? Blue, indigo, and violet, right? So even within the colors, there is differences, as I mentioned before, in terms of energy. This is the wavelength over here, like 700 nanometers, basically, for red, which is much longer than 400 nanometers on this side. And that means on the red side here, it's going to be lower in energy versus something that's more on the violet or purple side, or even the blue side is going to be higher in energy. So even within colors, we do see some differences in terms of the energy as well. By the way, in terms of colors and stuff like that, when we look at a color of a solution and it looks red to us, the wavelength of light that's being absorbed is actually not red. It's actually the complementary color to red, in the greenish sort of area and type like that, or greenish blue sort of area is really what's being absorbed. But to us, it appears we see actually the complementary color to what is being absorbed. Next to visible part of the spectrum is ultraviolet. So again, we're getting a shorter wavelength at this point, a lot more energy. This is why we put some sunblock on, right, when we go outside, so we don't get too burnt, right? They give you the UV index, right, and all that kind of stuff. And again, a lot of energy associated with that. Next to it is X-rays, also shorter in wavelength. A little bit higher in energy, which is why they throw a lead vest on you usually when you take an X-ray, right? And they leave the room, so they're not standing there when they shoot the X-ray. And then at the very end here of the electromagnetic spectrum, we do have gamma rays. Gamma rays are basically just pure radiation, right? Just pure energy. It's very strong, very penetrating sort of radioactive sort of ray. It could go very, very far in the skin and stuff like that. So this is the electromagnetic spectrum. You do need to know it. I personally am not going to ask you, for example, what the actual wavelengths are for any of these things, but you do need to be able to put these things in order for, say, which one it would be a longer wavelength or a shorter wavelength, higher frequency, lower frequency, higher energy, lower energy. So you need to know the order for that. I'm not going to ask you exactly where anybody breaks apart. In addition, you do need to also know that for the colors as well, which colors may be lower in energy versus higher in energy and that type of stuff. So you don't have to know the exact numbers, but you do have to know sort of the order: radio waves, microwaves, infrared, visible, ultraviolet, UV, X-rays, and gamma rays, and again, the colors. Any questions on that there? So again, everything to the left, shorter wavelength, higher frequency, higher energy. Everybody there to the right, opposite of that, longer wavelength, lower frequency, and lower in energy. So as we've been talking about, atoms and molecules can emit or absorb energy in these discrete quantities or packets of energy, which is our quantum of energy. And we could actually calculate the energy associated, for example, with a wave or even a photon of light by using this equation right here, which is E is equal to h times the frequency. H is Planck's constant, and it's 6.63 times 10 to the minus 34. Of course, they want you to know that one as well. So you do need to know that. So if you know the frequency of your wave, you can figure out the energy associated with it. By the way, we can also tie together this equation and the previous one. So if you remember, we had C is equal to the wavelength times the frequency, where the frequency is equal to C divided by the wavelength. And that means that if you take the bottom equation and you substitute this in for the frequency, you will get another version of this equation, which is hc divided by the wavelength. Why is that sort of helpful? That is helpful because h is a constant and c is a constant as well, which means if you know the wavelength, you could also calculate the energy associated with it. Or if you know the frequency, you could use the bottom version of that equation. Each one will allow you to get to the energy associated with that wave. By the way, the energy here will end up being in units of joules. So when you look at just the units here, H is joules times seconds, and obviously frequency is reciprocal seconds. So the reciprocal seconds and the seconds cancel, and that leaves you units of joules when you actually calculate it. Joules, as we talked about in the energy chapter, obviously is a unit of energy. Same thing happens up here if you use that version of it. H is joules times seconds. C is meters per second, and the wavelength is in meters. So again, meters will cancel, seconds will cancel, and once again, you'll be left with joules. So when you do calculate the energy using this equation, joules is the unit of energy that you end up with, typically speaking. Any questions on that? So again, what we're sort of referring to in this situation is, as we've been talking about, sort of that electron that goes up to a higher energy level and then comes back down, and that energy is being given off in the form of a wave as it transitions back down. By the way, when the atom gets rid of the energy, right, as it goes from a higher energy level to a lower energy level, that is an exothermic process, and you would get a negative number, technically speaking. And when the electron actually gains the energy to go to the higher level, it is a positive sort of situation that's occurring. So again, when you stick your flame tester into the flame, it's gaining all that energy. So the atom itself is gaining all that energy from the flame. Eventually, though, those electrons will relax back down, and then the atom's now going to release that energy as it does so in an exothermic type process. Any questions on that? This does give us, as we'll talk a little bit about, two types of spectrums. One sometimes referred to as an absorption spectrum, and that's the process where it's gaining the energy. And we typically, though, look at wavelength of 465 nanometers. We are looking for the energy. So that's going to be E is equal to H times the frequency. In this case, though, we don't have the frequency. You could, if you wanted to, get the frequency from the first equation, but you might as well just combo the equations together. So we could use the version of this equation that has the wavelength in it. H, again, is Planck's constant, 6.63 times 10 to the minus 34 joules times seconds. C is still our speed of light, 2.9979 times 10 to the 8 meters per second. Here again is where we want to be careful on units. We have nanometers there and meters there, so we do need to do the conversion. So again, nano being our 10 to the minus 9. So taking our nanometers and converting it into meters, 1 nanometer, 10 to the minus 9 meters, that is going to get us there. It'd be 4.65 times 10 to the minus 7, I believe. 4.65 times 10 to the minus 7 meters. So going into our equation, we will take our Planck's constant, 6.63 times 10 to the minus 34 joules times seconds, times our speed of light, 2.9979 times 10 to the 8 meters per second, all divided by our wavelength there of 4.65 times 10 to the minus 7 meters. Once again, here, seconds are going to cancel, meters are going to cancel. Going to leave us joules as the only unit left, which is good. Punching this in, definitely a exponent button situation here. 6.63 times 10 to the minus 34 times our speed of light. Hit equals divided by our wavelength. And looks like we will end up with something like 4.27 times 10 to the minus 19 joules in this case. Yeah. Any questions on that one there? So again, units, very common errors people make, as I mentioned before. You just got to make sure. All right, so on this one, we are looking for energy again. So we do have our equation, E is equal to H times the frequency. In this case, we are given the frequency. So really, in this case, we just need to plug it in there. Again, H is a constant. So using Planck's constant, 6.63 times 10 to the minus 34 joules times seconds, times our frequency of 2.87 times 10 to the 14 reciprocal seconds. Again, the seconds here are going to cancel, and that's going to leave us joules. So 6.63 minus 34 times 2.87 to the 14th. Going to get us here a 1.90 times 10 to the minus 19 joules in this case. Yeah. Any question on those calculations? So obviously you need to be able to calculate the wavelength, the frequency, or the energy associated with waves. Yeah. Any questions? Yeah. Well, on this one, probably those two are the ones you do need to know. This one and this one. Again, you could actually get you could get this one obviously from just substituting into here. So you can do it either way. You also, by the way, if you can't remember, you're not sure or confident, for example, that you would rearrange this one or substitute correctly. You could, for example, if you're given the frequency like we did in this problem, you could just use this equation here and solve for the wavelength if you're more confident doing it that way. And once you have the wavelength You can go into that equation if you wanted to. Actually, the previous one we were given the frequency in this case. Let me do it that way. So, if you're given, I guess, the wavelength, I guess is a way of doing that. If you're given the wavelength and you want to get to the energy, you could use this equation and solve for the frequency like we did earlier. That's what I was trying to do. And then you could go into that equation as well. So you could use those equations like that. You don't have to necessarily remember the last one, or you could just remember it or know how to kind of substitute it in would be a good one. So they do want you here to, again, know these equations. You do need to know the value of H, the value of C, those values as well. They do want you to know those guys. Other questions? Okay. All right, so as we've been talking about really throughout this, we're talking about really electrons as they transition from a higher energy level to a lower energy level. They do need to give off that energy in the form of light. And as we saw, that could fall anywhere on that electromagnetic spectrum. It could fall outside the visible part of the range, which you would not see color associated with it. But it could fall obviously in the visible part of the range as well. Now, as I mentioned earlier, what we typically look at are spectrums, and usually we look at the emission spectrums. As I mentioned before, there is what's known as the absorption spectrum, which is what happens when it absorbs the energy of the atom. But usually we kind of look at emission spectrums, which is, again, basically your atoms, electrons dropping back down, and the atom giving off that energy. Again, we can get this emission spectrum by doing something to energize a sample. For example, like your flame test, also like high electrical energy, like an electrical discharge lamp. Have you ever seen one? Like a neon lamp, basically, Vegas, basically, right? All those neon lights and stuff like that. That's basically what's happening. Those tubes are filled with elements and they turn it on, plug it in, basically. Electricity runs through it, excites it, and you get the neon colors and stuff like that. That's basically happening in that. We also don't do it at this school, but some schools do it in an experiment where you take lights like that, you put it in, you could look at it through a prism and you can see the different sort of lines and colors coming out at it when you do that. And when we heat up something, the red hot from an iron bar is the visible part of the spectrum where we see it glowing, but the warmth that's felt from it is also the infrared part of the spectrum. A common feature of the emission spectrum of the sun and heated solids is what is referred to as it being a continuous spectrum. And a continuous spectrum is typically what we see where basically everything just comes out at once. And that is different than what we see in a quantized energy. So earlier we talked about quantized energy being kind of like stairs, right? And either you're on this step, that step, that step, or that step. You're not going to stop anywhere in between the steps. And that's more of a quantized energy sort of example. Now, something like the sun in a continuous sort of spectrum, you could think of it more like a ramp rather than stairs. And if you walked up a ramp, right, you could pretty much lay up anywhere you want, right? You could stop anywhere along the way and you have everything sort of coming out at once, and it can't come out at once because everybody can kind of stop anywhere along the way. So you get like the whole spectrum basically coming out at once. And that is very different than what we see with atoms of elements. When they get excited, they do more of a quantized energy where, you know, they're either here or here or here. They have to be on a specific energy level, and they either has to gain or lose enough energy to fully transition, as I was mentioning earlier, from one energy level to the next. Mind you, by the way, when we're talking about these electrons transitioning, just like people that walk stairs, you know, it may be in a transition of like one energy level, or even like when people do stairs, they sometimes do two at a time, right? So electrons could go two at a time, energy levels 3, 4. So they could transition multiple sort of energy levels. Doesn't necessarily always have to be a one energy level at a time. It can go from like a first energy level to like the fourth energy level, or fourth down to the first and stuff like that. So it doesn't have to go down like a hit every energy level along the way. But as they transition, they will gain or lose enough energy to fully make, if they started up here, say at the fourth energy level and went all the way down to the first, they will lose enough energy to get all the way down there. They won't stop in between, basically, along the way. And again, that's the idea of quantized energy. Now, the emission spectrum of a continuous spectrum will show you sort of everything. But atoms in the gas phase, when you sort of excite them, will give you that more quantized energy. And you get a different type of spectrum. You get what's referred to as a line spectrum. And much like it sounds like, it is a bunch of lines that you would see if you looked at it, for example, through like a prism. And these lines would have different colors, and they would actually correspond to different electrons transitioning from different energy levels. And they would occur at different wavelengths. And a line spectrum is something that is actually very unique for every element. So each element will have its own unique line spectrum. So based on the colors that you see, based on the wavelengths that you see where they're coming out, it will tell you, you could figure out what element you're looking at based on that. So kind of like a fingerprint, if you will, every element has its own sort of identical, or identical, own individual, it's the better word there, individual sort of line spectrum that is different from other elements. And that is sort of how we can see a line spectrum. We take a lamp and excite electrons, look at it through a prism, it will separate it out. And this is, again, more of a continuous spectrum, as you can see there, versus what we see with atoms, this more line spectrum, where we see distinct colors occurring at distinct wavelengths. And again, each of those lines, as I mentioned before, corresponds to different electrons transitioning from different energy levels. Take a look at that.
When the light emitted by a hydrogen gas discharge tube is passed through a prism, a line spectrum results. This line spectrum consists of light at only 4 wavelengths in the visible region.
Now, here is hydrogen's line spectrum. And we could also, for example, based on what we were talking about in terms of energy and wavelength, we could also make some pretty good estimates, for example, of how far these electrons are perhaps traveling. We know from our conversation that red is lower in energy, right, than, say, our purple guy over here, right, which is higher in energy. That would also mean that perhaps the transition that is causing us to see the red color is maybe just a transition of, say, 1 energy level, right? Not very big amount of energy difference between those. As opposed to over here where we see this purple one, maybe that is a result of an electron making a pretty good jump downwards or drop downwards in energy and going through a lot of different energy levels. So, you know, this guy on the left here would probably correspond to a greater number of energy levels that that electron has passed to get to the bottom or wherever it ends up, versus over here on the red where maybe it's a much shorter transition for that electron that's occurring. Now, one explanation of those lines that we see in hydrogen was done by Bohr and Bohr's model of the atom. And Bohr's model of the atom dealt to explain the 4 lines that we see in hydrogen. And it works really well for hydrogen, but it is a theory. And if you remember at the beginning, theories are things that can be revised over time. And that is what happened with Bohr's model of the atom. Bohr's idea of the atom, hydrogen atom, worked really well to describe sort of what's happening with hydrogen and those 4 lines. As we sort of move away from hydrogen and we get a lot more electrons involved, it doesn't really hold up. And again, we kind of move away from his model. One of the idea of his models is this sort of the planetary model where we have the nucleus in the middle and we have these orbits where electrons are traveling. And his idea is that these electrons are in these fixed orbits, and moving around in pretty little circles and stuff like that. And what we're seeing as a result of those lines is, for example, an electron moving from one energy level to the next, yeah? And that is accounting for those sort of lines that we see in that spectrum. Now, one of those ideas is, as we will talk about, we sort of move away from this idea of these circular orbits, but this was his idea. They could only be located at certain distances from the nucleus. So again, with our orbits here, our electron would have to be in this orbit, or however many orbits I could draw here, that orbit, and they would be moving around. Again, same idea. They would gain and lose enough energy to fully transition from one orbit to the next. And as they are moving from those orbits, again, that is what's causing those different lines that we see in the line spectrum. And as I mentioned, we got that transition coming down, and perhaps this is what is causing that red line that we see coming off that corresponds to that energy as that photon goes to a lower state of energy. Now, when we talk about energy levels, there is what is referred to as the principal quantum number, which is n. N is the abbreviation for principal quantum number. There's actually 4 quantum numbers. We really don't get too far into quantum numbers in here at all, but when you take 1A, you'll learn about the 4 different quantum numbers. But basically, N is the principal quantum number. That is a fancy way of saying the energy level. It's basically the fancy way of saying we're talking about the energy level. N could have values of 1 through 7. So there's basically 7 energy levels where we can find electrons. And an N equals 1 value is what is referred to as the ground state, or the ground level. It is the one that is closest to the nucleus. It is the most stable sort of energy level, right? Because it's lowest in energy. As we will talk about, electrons do kind of feel lowest energy to highest, and the lower the energy level, the closer to the nucleus it is. Anything above n equals 1, anything from like n equals 2 through 7, those are what is referred to as the excited states. And those are typically higher in energy. And they are also, as you continue up, sort of further away from the nucleus as you go through it. Questions on that there? So as we talked about earlier, again, you can see here our red transition, a much smaller transition. So probably corresponds to lower in energy than here our blue, which obviously had a lot longer of an energy transition. Again, higher in energy, longer in energy, going to result in a shorter wavelength and more of a blue color than, say, that shorter energy transition that we see here for red, which results in that longer red wavelength that we see. And again, as we talked about with Bohr's model, each of these transitions would basically represent those different 4 lines that we saw. Again, the shortest transition probably going to be our red. The longest transition, which kind of looks like this guy, is going to probably be our one that's responsible for the purple or violet colored line that we see in the spectrum as well. On the left, again, is a continuous spectrum. And again, you can think of it as you pretty much get energy anywhere along the way, as opposed to these very distinct energy levels that we see in a quantized energy like n equals 1, n equals 2, n equals 3, n equals 4, where we would find electrons. So again, in a quantized system, we would find electrons here, 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 or here, nowhere in the empty space in between, as opposed to in a continuous spectrum, we can pretty much find anybody anywhere along the way of the journey. Hence our stairs versus our ramp illustration. So Bohr's model, as I mentioned, really worked well for hydrogen, but as I said, as you sort of get a lot more electrons sort of into the mix, it really didn't hold up very well. And we sort of transitioned from sort of the idea of Bohr's model and these orbits to what is sometimes referred to as a more wave mechanical model of the atom. And one of the first sort of movement towards that was de Broglie. And de Broglie actually didn't do the experiment. He actually just sort of theorized it. Somebody later on did some experiments that kind of proved him right. But de Broglie sort of came up with this idea of, again, as we talked about, this sort of dual nature that particles like electrons could behave like waves, and waves could have particle-like function. So what he talked about was this idea of basically particles like electrons behaving like a standing wave, right? And if you have a standing wave like on a guitar string, right, and you pluck it, you will have basically a wave that occurs. But your string is not going to go anywhere because it is attached to the guitar, right? So hence the standing wave. So if you pluck it, you'll get the wave that will occur. And that's sort of how he envisioned sort of electrons here, that even though electrons are particles, it can have this sort of standing wave type function that can occur. And when we think about it, right, we have a nucleus which is positively charged. We have these electrons which are negatively charged. So once again, as I mentioned, there is going to be sort of that attraction between the electrons and the nucleus that's going to kind of keep it there. And as they're moving around, they're going to kind of move around in this sort of standing wave type of idea that it can't escape because it's sort of tied like the guitar string is to the guitar. It's sort of tied to the atom through the nucleus, right? This sort of attraction force between them. And what he said was when you look at a wave like that or a standing wave, there are some points, for example, that have no amplitude, right? And these are what are sometimes referred to as nodes, and these are points where there is no amplitude there. One of the ways we sort of think of like sort of the nodes is kind of like where the nucleus is, sort of where it's kind of holding the electron in place, if you will, as it's moving it around. So what he thought was that waves can behave like particles, and particles like electrons could have this wave-like function. And this was an important step. And the next sort of important step that kind of moved us again away from Bohr's model of the atom and this for sure idea of in Bohr's model, I have these orbits. I know, for example, my electron has to be in the orbit. And if I put my finger right about there, at some point I know the electron's going to come around the circle, right? And eventually will be there. And it has sort of a known path. It was sort of Bohr's idea. Now, what kind of moved us away from that as well is what is known as Heisenberg and Heisenberg's uncertainty principle. And Heisenberg's uncertainty principle basically says that it is impossible to know simultaneously both the momentum and the position of a particle at the same time. And actually, the more you know about a particle's position, the less you know about how it's traveling, and vice versa. The more you know about how it's traveling, the less you know about its position. And what this is moving us away from is this idea of Bohr's model, where we know for sure the electrons are traveling these pretty circles, to this idea of we really don't know how the electron's traveling. And the more we know about how it's traveling, the less we know about exactly where it's positioned, and vice versa. So this was an important step sort of to move us away from Bohr's idea of this planetary model. And sort of the last sort of major step that moved us away from Bohr's idea of these orbits was one that's known as Schrodinger's equations. And if you ever take physical chemistry, which most people take at the very end of their chemistry journey when they go to school, they push it off as far as possible. You'll learn all about it. It's a bunch of calculus and theoretical type of derivatives and stuff, calculations that you do. But instead of knowing, since we don't really know how electrons are moving, we don't really know exactly where they are at any given point in time through Heisenberg's idea, what the idea is, the best we could do is predict a high probability of where you could find an electron. And again, a high probability of where you can find an electron doesn't mean we know exactly where it's at. It just means if we had to take a pretty good guess, we should be able to find an electron at a certain spot within the atom. And if you think about the electron and the atom, there should definitely be a pretty high shot of finding an electron near the nucleus. Again, because of the attraction between the positive nucleus and the negative electron. As you fan out from the nucleus at some distance, the probability is going to start to decrease. There's going to be less of a probability of finding electrons further away from the nucleus. Does that mean you cannot find an electron far away from the nucleus? The answer is no, you can. Just as you're going to have probably a lesser of a chance of finding it than you would if you're like right next to the nucleus, right? Because there's going to be a lot more attraction towards the nucleus. So these three guys, sort of de Broglie, Schrodinger, and Heisenberg, moved us away from Bohr's idea of orbits to a more theoretical sort of description of where we find electrons in an atom. And these are what are referred to as orbitals, or atomic orbitals. And we're going to talk about some different types of atomic orbitals. There are s orbitals, there are p orbitals, there are d orbitals, and there are f orbitals. And these are all sort of theoretical sort of probability maps within an atom where you could find an electron in terms of a high probability. Again, we don't know how it's traveling. We don't know exactly where it's located. But if we had to throw a dart at the board there and try to find where we could find an electron, there is a better place to throw your dart than somewhere else. And if we take a look at this, you can see here the darker area here, which you can think of the nucleus in the middle. This darker area is a much higher probability of finding an electron. And you can see as you sort of fan out from the nucleus, it gets lighter, and again, a lower probability at that point of finding perhaps an electron. Again, you could definitely find an electron out there, but the probability would be much less than closer to the nucleus. And once again, this is all the empty space that we talked about with Rutherford, right? And in this empty space, we basically got random sort of electrons moving around. Again, not in pretty orbits and circles, pretty random type of movement. Any questions on that there? So then let's talk about the atomic orbitals, which is where we sort of probability maps of finding electrons. Let's just start with, first off, the basics of orbitals. And the basics of orbitals are this. Any orbital, any individual orbital that you have, and I'm going to represent that by just a line as the orbital, it could hold a maximum of 2 electrons. So any individual orbital could hold a maximum of 2 electrons. I'm going to use the arrows to represent the electrons here. So 1 electron, 2 electron. So any individual orbital that you have, that is the maximum number of electrons that you could put into an atomic orbital. Do you have to put 2 in there? The answer is no. You could have some that are empty. You could have some that have 1 electron, and you could have some that have 2 electrons in there. But you cannot have more than 2 electrons in an individual orbital. So let's talk about where we find these. Let's start with really the basic orbital. And when we talk about our energy levels here, remember that is the quantum number of n. N equals 1 is the lowest energy state you could have. And s orbitals start at the n equals 1 level. So at the very first energy level, you will have s orbitals. They will actually be called a 1s orbital on the first energy level. And you will have s orbitals on every energy level. So on the second energy level, they would actually be called 2s orbitals. And the 2 is equal to the energy level, or the principal quantum number. The 1 in the first one is equal to the n number as well. S orbitals are merely spheres. And when we talk about the type of orbital, which is an S, how many orbitals there are? There's only one type of s orbital. So no matter what energy level you're on, there will only be one type of s orbital. And because there's only one type of s orbital, it could hold a maximum number of electrons of 2. And that means, for example, I could fill up on the first energy level that orbital with 2 electrons. On the second energy level, I could only fill it with 2 as well. By the way, if I went to the third energy level, it would be known as a 3s orbital. If I went to the fourth energy level, it would be known as a 4s orbital. So you will find s orbitals on every single energy level. And again, the number that comes in front of the letter represents what energy level it's on. Any questions on that there? So here is what theoretically a s orbital looks like.
An s orbital has a spherical shape with the nucleus at the center.
So again, anywhere in there is a probability of finding an electron. Again, near the nucleus would be, again, a higher probability of finding an electron than maybe further away. Here again is our high probability in the center there near the nucleus where we'd find our electron. All s orbitals, no matter what energy level, are the same shape. They're all spheres. They just get larger as you go up in energy levels to accommodate all the electrons that there are. The next type of orbitals are actually p orbitals. And p orbitals start on the second energy level. So they start on n equals 2. So if you take a look at what we were just kind of drawing there, our n equals 1. The only thing on that energy level is a 1s orbital. When we get to the second energy level, we still have an s orbital. And this is where we start to see p orbitals occur. And they're referred to as 2p orbitals. Now, in terms of p orbitals, how many p orbitals are there? There are actually 3 different p orbitals. There are a px orbital, a py orbital, and a pz orbital. And that basically, if you think about math, there's like an x, y, and z coordinate plane. They're all sort of in 3-dimensional space and different orientations. Now, because there are 3 individual p orbitals, the maximum number of electrons, if you filled up all 3 of those p orbitals, is 6. You could pop in there 6 electrons maximum in a p, what is referred to, by the way, as a p subshell or a p sublevel. So all 3 of these p orbitals, which are on the same energy level, these are what are referred to as a p subshell. Some books will call it a p or a 2p subshell, if you want to get more specific, a 2p sublevel. So a subshell or a sublevel represents a grouping of multiple orbitals that are the same on the same energy level. So if you maxed out the 2p subshell, you could put 6 electrons. Once again here, you don't need to max it out. You could have anywhere from 0 to 6 electrons in there, in that 2p subshell. Any questions on that there? What do p orbitals look like? People describe them as teardrops or kind of figure 8s, if you will. So they look like figure 8 type of pictures, as you can see here.
The 2px orbital is in the shape of a figure 8 along the x-axis.
So kind of in the center here is, you could think of the nucleus. I don't know if it'll let me write on this. I'm not sure. I don't think it will. But kind of in the center, I don't think it will. You got this kind of deal happening. Kind of in the center is like the nucleus, and then you could have an electron anywhere in that sort of empty space there is possibly where an electron could be. This is the 2y, py, which looks the same.
It's in the shape of a figure 8 along the y-axis.
And then obviously we have a 2pz.
The 2pz orbital is in the shape of a figure 8 along the z-axis.
And again, each of these 2p orbitals can hold a maximum of 2 electrons. And again, since there's 3 different ones, 3 times 2 is 6. And that is how we max out all 6 if you fill up the entire subshell, which consists of all 3 of those p orbitals together. Any questions on that there? And again, as you can see here, this sort of area is the highest probability of finding electrons in these orbitals. And again, kind of think of the nucleus sort of in that spot right there. The next type of orbitals that we see occur actually on the third energy level, and these are d orbitals, and they start on the third energy level, n equals 3, basically. So once again, here we have on the first energy level only an s orbital, on the second energy level an s orbital and our p subshell. On the third energy level we have s orbital, p orbitals, and this is where we first start to see d orbitals basically appear. So it's not to the third energy level that we actually get the d orbitals happening. There's actually 5 different types of d orbitals. So for d orbitals, there's actually 5 types. And because there's 5 types, basically 1, 2, 3, 4, 5, each one could hold 2. So if you filled this entire subshell or d subshell up, 5 times 2 is 10 electrons maximum if you filled up the entire d subshell. Once again, you do not need to fill up the entire subshell. It could have anywhere from 0 to 10, obviously, the subshell. And this is all these individual d orbitals, which are right here in this picture. You can see for the most part, most of them look like 2 p orbitals stuck together, except for this guy over here, which they describe as like a donut with a p orbital going through the middle of it. And again, each of these could hold 2 electrons maximum. So 2, 4, 6, 8, 10 total electrons at this point. Here's what they look like.
Lies in the XY plane and is aligned along the X and Y axes.
The 3dxy orbital has a cloverleaf shape that lies in the xy plane and bisects the x and y axes. The
3dxz orbital has a cloverleaf shape that lies in the xz plane and bisects the x and the z axes. The 3dyz orbital has a cloverleaf shape that lies in the yz plane and bisects the y and z axes.
The 3dz squared orbital is shaped like a pz orbital with a donut of electron density around the center. It is aligned with the z-axis.
And again, all that green spots obviously in these animations are the probability or electron density. Darker areas, again, higher probability of finding electrons. Lastly, in terms of orbitals that we deal with are f orbitals. And f orbitals do not start until you get to the 4th energy level. So f orbitals start at the n equals 4 level. Once again, kind of building our thing here. First energy level, 1s. Second energy level, 2s and R2p. Third energy level, 3s, 3p, 3d. And now at the 4th energy level, we still have 4s, 4p, 4d. I don't know if I have enough room, but I'll try. 1, 2, 3, 4, 5, 6, 7. And that is where our 4f basically first starts to appear. As I just mentioned, there are 7 different f orbitals. Again, each one could hold 2, which means if you filled up the entire f subshell, 2 times 7 is 14 electrons maximum. So you could put in there 14 electrons in there.